So tonight we're going to hear about ocean acidification, and then we're going to hear about coral reefs and the major threats to coral reefs, one of which is ocean acidification. Our two speakers are both professors from Scripps, and Dr. Todd Martz is going to go first. And you have their bios in your packet, so I'm not going to go through all of these, but just let me make a couple of comments. Todd, and they've both been at Scripps now for, what'd you say? 10 years. 10 years? 9 years. 9 years, okay. And they went at the same time. And Todd had been at MBARI, that all of us know well, the Monterey Bay Aquarium Research Institute, and he was one of the beneficiaries of the Ocean X Prize on pH measuring devices. And Jennifer Smith, her lab studies coral reefs all over the world and looks at the different threats to them, ranging from warming of the ocean, ocean acidification, but also things like fishing and coastal development and pollution. So Todd is going to go first, then we'll take a break, and Jennifer will tell us about the world's coral reefs. So please welcome Todd Martz.
Thanks, Jerry, first of all, for the invite. We had a nice time walking around, checking out the aquarium. Really beautiful. So I'm a chemist by training, and I'm going to talk to you a little bit about marine chemistry, just to start off. And I've kind of thrown in 3 different topics here, which I hope, they have some overlap, but I hope it's not too all over the place. But chemistry background and talking about ocean acidification, which really falls under the larger umbrella of the carbon budget. So I'm going to talk to you about the carbon budget a little bit today. And then an overview of CO2 measurement technology, which is really where I work. I focus on a lot of the engineering and developing new technology, sensor technologies. And then I'll try to pull it together with a discussion about some observing programs, past, present, and future. So if you haven't thought about marine chemistry in recent years, this is just a refresher slide to get us thinking about what's in the seawater. And when we talk about salinity, we're talking about the fact that there's about 35 grams of seawater in of salt in every liter or kilogram of seawater. And most of these things constitute sea salt, only a handful of things that behave relatively conservatively. And there's this little 0.7, less than 1%, labeled minor constituents, which is actually what most of us are really interested in. That turns out that this is where all the climate controls come in. So the carbon system, which is what I'm focusing on, is about half of that 0.7%. And this is just the backdrop for the CO2 system in the ocean. What you're looking at here is 2 contour plots of concentration. So red numbers being high, purple being low concentrations of the total amount of CO2, carbon dioxide, at the surface of the ocean and at the bottom of the ocean. Okay? And there are a couple of things just to note here. The numbers don't make a whole lot of, it's not that important right now that you understand what those are, but remembering that that's that fraction of 0.7%. This is in micromoles per kilogram. But at the surface, the total carbon is controlled by different processes at the bottom. So this is just kind of interesting to note that you have things like broadly lower total amounts of carbon across the equator where temperature is high, and higher amounts at the surface where temperature is low. That means this really means that CO2 is controlled primarily over large scales by solubility effects, but also biology drives it a little bit. At the bottom, we really see the pattern of biology driving what we refer to as the ocean conveyor belt. So as the seawater circulates around from the North Atlantic through the Southern Ocean to the North Pacific, remember this is at the bottom, you have an accumulation of CO2 at the bottom. And this is tracked through this ocean conveyor that the physical oceanographers taught us about. And I have just a few slides with some chemical equations, but there's not going to be much of this. Just bear with me for just a couple of slides here. But I want to just walk you through a couple of simple chemical reactions. CO2 in the atmosphere dissolves into the surface ocean and it reacts with water. So this is a hydration step, forming carbonic acid. And then there are two what we call dissociation reactions, where carbonic acid gives up a proton to form bicarbonate. Bicarbonate gives up a proton to form carbonate ion. Okay? You don't have to understand everything on this slide, but it's worth noting that there are 4 measurable terms. We call it sometimes master variables of the CO2 system. These are the partial pressure of CO2, the total dissolved inorganic carbon, the total alkalinity, which is really the carbonate alkalinity is what we're interested in, and the pH, or the hydrogen ion concentration. If you recall, if you've ever seen pH written out, it is just a concentration, but it's in the log form. I noticed that when I put this talk together that some of the terms get confusing because different figures that I've pulled from different sources tend to use different expressions to all mean the same thing. So if you get confused, you should just ask, go ahead and feel free to ask a question if something doesn't make sense. But sometimes this term I've referred to as C sub T for total inorganic carbon might be one of these other things, but it's always the same thing in these slides. I'll try to remember to point that out. But remember, we don't have to remember everything in this slide, just that there's these few terms that I'm going to talk about in the context of ocean acidification. So I bet you've already seen this figure at some point, maybe every single lecture so far. But the Keeling curve, we know about Dave Keeling, started measuring atmospheric CO2 back in 1957, I think. There's a corresponding set of ocean chemistry measurements that began right around 1990, late 80s. And these are taken from seawater at Station Aloha. So the classic Keeling curve that you know is sampled in the atmosphere on top of Mauna Loa. The Station Aloha has been going on now for 30 years or so, and they go out and sample the seawater. And you can see the seawater tracks the rising CO2 in the atmosphere. And what you're looking at on the right side here is the pH going down in the blue, and the PCO2, which is labeled CO2 here, which is the partial pressure of CO2, in the seawater is tracking that in the atmosphere. And I just wanted to make a note here that the Scripps carbon dioxide program really drove these measurements, but they're now made globally by many different labs. Andrew Dixon is kind of carrying the torch at Scripps right now, and he's the one that's responsible for the global supply of reference materials that make these high accuracy measurements possible. And if you're interested in some further reading, there are a few sources that you could look up that sort of summarize in great detail the few slides that I just mentioned. This is the authoritative guide that Andrew Dixon has worked on for a couple of decades. This is a textbook, and this is a kind of a spin-off guide to best practices. This is how to make really good chemical measurements. This one's how to design ocean acidification experiments aimed more at biologists. I think it's the last chemistry slide that I have, but in order to explain, I lied, there's a couple more, but in order to explain ocean acidification, a useful figure is a log-log concentration diagram. So what this is showing you is the chemical speciation of the CO2 system as a function of pH, okay? And remember that I talked about this total amount of CO2 in the ocean. That's the 2 contour plots that I showed. In this example, this is a constant number across this whole range of pH, but these different ions are contributing to it at different proportions depending on what pH you're located at. So the ocean is always in this range of about 7 to 9 pH units. But what you can see is as you shift pH to a slightly lower value, you would expect to see a shift down in the carbonate ion and up in the bicarbonate ion. Can you see that? That if you start moving that way from high pH, you're going to be turning this carbonate into that bicarbonate. And that's an important thing. It's an important thing to remember for ocean acidification. There are a couple slides here that I pulled from Dick lecture that Dick Feely and Scott Doney put together. You could find this on the ASLO website, and you could also find maybe this on the Pacific Marine Environmental Laboratory website that PMEL runs. But just kind of an example of showing cartoons of the chemical reactions that I just showed you. And this is essentially showing another diagram of chemical concentrations. Showing these reactions, I showed you these before, but carbon dioxide turning into first carbonic acid, which dissociates, and then the bicarbonate ion actually reacts with a carbonate ion. This is just a slightly different way to think about how these reactions couple with each other. But the net reaction, so this isn't an elementary reaction, but it's what we call a net reaction in chemistry. That marine chemists like to think about is that carbon dioxide is reacting with carbonate to form more bicarbonate. And what that's doing, if we think about this in time, as we add some CO2 to the ocean, pH and carbonate ion are going down. You can read that on the right axis. And we think they've already gone down by about 16% for carbonate ion up to the year 2000. And the acidity, in this case, which is the pH, has gone up by 30%. And by 2100, those numbers would be something like 100 to 150% increase in acidity and a 50% decrease in carbonate ion. And this is important, people think, for organisms that form calcium carbonate shells. This is a terminology that's often employed by marine chemists called saturation state. We use an omega. And it's a unitless number that it's calculated unitless because you're taking the ratio of these chemical concentrations to this constant, which is actually these two concentrations at saturation equilibrium. So when you add a mineral to some water and you stir it around, some dissolves up until a certain point, it quits dissolving. That's saturation equilibrium. And the only thing you have to remember about that is that omega equals 1, you're at equilibrium. Greater than 1, you have supersaturation, and calcium carbonate can freely precipitate. Less than 1, calcium carbonate should dissolve thermodynamically. And in the ocean, we actually have, in most places, omega greater than 1. As we add CO2 to the atmosphere and it dissolves in the ocean, that omega drops closer to 1. This is about the only biology slide that I'm going to show. I'll let Jen take the rest of that for her talk. But just because I showed you the omega slide, one thing that's been done by a lot of people studying ocean acidification is to test how various organisms grow under different saturation states, under different omegas. And the confusing result at this point in time, at least in 2009 when this was published, is that different organisms may have a positive response, they may have a negative response, they may start with a negative response and end up with a positive response. So it's a confusing situation to try to understand how an entire ecosystem is going to behave as we acidify the ocean. And that's kind of the state that we're at right now. The last thing I want to just kind of transition, pulling slides out of Dick Feely and Scott Doney's presentation, is this penetration of anthropogenic CO2 into the ocean is not evenly spread around the ocean. Okay? It is going in at the surface, but as the ocean mixes differently at the high latitudes versus the equator, that penetration of anthropogenic carbon may be restricted to the upper 100 meters or so in some areas. It may be getting down into the 15 or even 2,000 meter depths in other locations. And this has some effects on that omega. It's essentially making that number go down at all of these depths where the anthropogenic CO2 is penetrating. It would potentially be affecting any organism that's forming a calcium carbonate shell. Moving on from this slide on anthropogenic CO2, I want to just show you a few things about the carbon budget that you may or may not have already seen. But I've thought about this, I guess, for years, but I have kind of got re-interested in it last year when I went to the COP meeting. They publish this every year. This is the most recent publication, the Global Carbon Budget 2016. This is not just ocean, but this is all of the reservoirs in the active biosphere. So if you're interested in reading more on this, here's a good resource. And these are tied together. The Carbon Atlas shows kind of active fluxes based on nations. And so they generate products like this that show the basic 5 different reservoirs that scientists like to think about. You've got the big fossil fuel industry putting CO2 out into the atmosphere. and some other land use change, and then the three different sinks, the atmosphere, the land, and the ocean. And the goal of these publications is to quantify these numbers, right? So how much per year is going out or going into a given reservoir. And we actually know the emissions really well. We know this number better than anything else because this is money, right? This is how much oil we're selling and burning and gas and all of that. And there's a small uncertainty on it because we're lumping in things like land use change that people have to get at through approximations using like satellites to look at how land's changing. But we know the emissions number really well. And what we don't know is where the emissions are headed into the future. It's anyone's guess, right? Here's all the hundreds of projections that people make. But right now, it seems that we're a little bit closer to the top end of the range of projections that people have been making for the next, for the rest of the century. The numbers that they come up with at present show that out of the CO2, these are gigatons of CO2. So out of the 34 plus 3.5 gigatons per year that are going in, they get partitioned about like this, 44% into the atmosphere, 31 into the land, and 26 end up in the ocean. In fact, given long enough periods of time, almost all of that will end up in the ocean. But it takes like things on the 1,000-year time scale for it to mix into the ocean. And this is just another picture showing how these emissions have grown since 1880, so halfway through the Industrial Revolution. And we are, like I said, we know this number really well. We approximate this number to some extent. The atmosphere number we know really well because the atmosphere is really easy to measure. You think about how the atmosphere mixes. It's like you could probably have one measurement in the atmosphere and get a pretty accurate number because it mixes annually. Ocean, on the other hand, takes about between 1,000 and 2,000 years to mix. So much more difficult to measure the ocean sink compared to the atmosphere. So where one measurement in the atmosphere can get you a lot, you need probably hundreds or thousands of measurements in the ocean. But they actually have made enough measurements now to come up with numbers for the ocean sink. Turns out the land is the one that we have really no measurement for. Land is the residual here. So we're not really able to even measure the land sink at this point. These lines are showing how those sinks are growing. So what I mean is how this line, this blue line for the ocean is expanding. How that rate is expanding is the slope in this line. Okay? And one thing that scientists that are modeling the climate are concerned about is, will these remain steady or will they begin to drop off? We don't really know, but people do think that with climate changing, these rates of increase cannot remain steady for centuries. They must trail off, if not decrease. So they're worried about that. This is in thinking about the cumulative concentrations in terms of the concentration of CO2 in the atmosphere. So we were at 288 parts per million CO2 in the atmosphere at the beginning, or in 1870. We're now at 400, and these are the contributions from the different components of fossil fuels and the subtractions due to the different sinks. There's the ocean sink. And the number that I wanted to just point out to you when we think about this in terms of gigatons of carbon, this about 600 or so is the total amount that we've put in, we think, since the beginning of the Industrial Revolution. And most of that's happened in the last 140, 150 years. So that 600 number puts this into context. When you think a little bit about why scientists are so concerned about adding CO2 to the atmosphere, we start to think about geological time. And so if you go back 500 or 1,000 or 1,000,000 years and look in the ice cores, you can find these oscillations that are due to the orbital variability of the sun, or the orbital variability of the Earth around the sun causes these Milankovitch cycles. And we know that we've added this amount of CO2, and we're outside of this range over the last 1,000,000 years. And what's really scary is when you go back even further and you look at an extinction event 55 million years ago, for example. We call this the PETM. Looking in cores, in sediment cores, there's this really stark transition that happened, which was some type of an extinction event at 55 million years. And just for dramatic effect, here's the author of the science paper in his wetsuit holding the core. as if, I guess he dove down and got the core at the bottom of the ocean. I don't know. But yeah, so Jim Zakos dove to 2,000 meters and cored that thing. And what this tells us is that we look at two different things in these cores, but this term that says del C13 is telling us something we think about, and a huge input of maybe organic carbon into the biosphere. And that would be analogous to burning a lot of fossil fuel. And what this shows is calcium carbonate weight percent in the core. So if you look at that, there's a bunch of calcium carbonate in this core, and then there's none, and it just goes away. And that's what's happening right here. You've got going from 80, 90, maybe close to 100% calcium carbonate, boom, and it's all gone. And it takes something like, I don't know, 100,000 years to get back to normal. And this event seems to be sort of what's happening now. We don't know exactly how much was put into the atmosphere to do this. I actually just saw in Nature or Science, there was a paper that came out last month with co-authors at Scripps saying that they think maybe as much as, I said several thousand, did I say that here? Several thousand petagrams, they think maybe 10,000. But the point is, we put in something like 600, we're on our way. So, big shift now. So that was just the some background on carbon budget and ocean acidification. Things that I find interesting to try to set the stage for why we spend so much time working on measuring it well and developing new technologies to track CO2. And so I'm going to maybe show a couple things from my own work, but I try to throw in some slides from my colleagues and various other people. So why do we need new technology? The ocean is chronically undersampled. We need to both improve existing technology, like what we're already using, and benchtop and underway systems. I'll explain those in a minute. But we also need to develop new autonomous platforms and sensors. This has been discussed by myself and several other people in recent articles over the years. I want to just give a few definitions. As I talk about these instruments, I like to categorize them as benchtop, which would mean things where I get a bottle of seawater, I bring it to my lab, I make a measurement on the benchtop using some kind of system that's in the lab, or maybe on a research vessel. Underway is automated, so you're on a research vessel probably, or maybe a shore station, but you're pulling water in, you're pumping water in, and it's continuously measuring and it's generating data, sending the data somewhere or logging it. You're getting a continuous stream of underway data, probably from a moving platform. Autonomous systems are completely standalone. They have a computer that's logging the data. There's no human operator involved. And they're on some type of a totally autonomous platform, is my definition. So that would be like a buoy or something in the ocean. And sometimes people get remote sensing confused, but when I say remote sensing, I'm talking about satellite measurements. This is from a paper that I wrote a couple of years ago that categorizes, remember I said there's these 4 master variables, the measurable things of the CO2 system, and I've screwed up because I've written DIC instead of C sub T, but this is the total amount of carbon, total alkalinity or the carbonate alkalinity, pH, and the partial pressure of CO2, categorized by level of autonomy. And one thing that jumps out is that not all these boxes are filled. If some of my colleagues were here, they'd be very quick to point out that people have published papers in every box here, for sure. What I'm showing is what's commercially available. Okay, so this is what people are pretty much restricted to nowadays for observing the CO2 system in the ocean. And these boxes that are unfilled are things that people like myself are working on. We'd love to build an autonomous dissolved inorganic carbon measurement and put it on some kind of an autonomous platform. This is the type of instruments that I'm talking about that sit in my lab and other people's labs. This is Andrew Dixon's lab at Scripps. It says a titration system used to measure total alkalinity. This apparatus does the DIC or the C sub T, the total amount of inorganic carbon in the sample. And this actually does the same measurement as this, except it uses a different detection scheme at the end. So this is an infrared gas detector, and this uses what's called a coulometer. So kind of complicated. systems, lots of tubes, lots of points of failure is the reason I'm showing this picture. They work when you have an expert operator. Very difficult to turn this into a completely underway or even an autonomous system. There are a lot of very successful underway measurements that measure the partial pressure of CO2 all around the surface ocean, and that's because it turns out PCO2 is probably the easiest. It's arguable, pH is pretty easy too, but PCO2 is one of the simpler measurements that you can make. You can set up a continuous flowing line with some kind of a air, gas, liquid equilibrator and a detector, and you're on your way and you're making underway measurements. My friend Alex Wang has built very more complicated systems to measure other parameters of the system, like dissolved inorganic carbon. But as you can see, it kind of takes Alec to run it. Right? It's more complicated. This is a little bit more in my realm. I've done some work with pH sensors, actually in both of these areas. But pH it seems like it's an easy measurement to make, but there are some pitfalls that people can make. But this is really divided into two different types of instruments that are either spectrophotometric. So if you think about litmus paper that we use to measure pH, what marine chemists do is they take the chemical on the litmus paper and they dissolve it in water. They put a little bit in seawater and then they put it in a spectrophotometer that measures the absorbance spectrum. You can get repeatable measurements into the 4th decimal place with this. It's the gold standard for pH measurement in the ocean. You like 0.0004 pH unit resolution. It's amazing. You can actually do really well with potentiometry, which is even simpler. So a glass electrode, you literally just put in your sample and it gives you back a number. Does it always give you the same number? Does it drift? So we have to worry about things like instrumental drift a little bit more in these. And I'm going to show you a few more slides talking about this ISFET technology, which is one thing that my lab has focused on in recent years. But it is a nice, simple measurement because you just have pH and you have a voltage that comes out. And usually you can make it a really straight line if you understand some of the nuances of how the sensors work. This ISFET stands for Ion Sensitive Field Effect Transistor. Is a technology that was developed in the late 1970s, and Honeywell really pushed it to a high level of operation, and it's replaced the glass electrode in many laboratories and industrial settings. And so we had adopted this and started to put it in seawater. I had the good luck to work on a spectrophotometric autonomous sensor as a graduate student, which was this paper back in 2003, and then move over and start working on the ion-sensitive field effect transistor. So the SAMI is the Submersible Autonomous Moored Instrument for pH. And we call this the CFOX because it measures, I guess, pH and oxygen. We have an oxygen sensor in there. But I worked on these two papers, so I kind of did both ends of the pH measurement thing, and we ended up, like Jerry mentioned, we ended up competing those two against each other in the X Prize. And my graduate advisor, Mike DeGrand-Prix, won the X Prize, and we took second with the ISFET sensor. But these ISFETs have been really useful in a variety of different designs because they're so low power, easy. It's a solid state sensor, no moving parts, pumps and valves and all that. So it has really been latched onto by the oceanography community. We've now put them in a variety of different packages. And this picture at the top is the chip itself. It's about 2 by 3 millimeters. And this is just kind of the history of where those are now. They're commercialized and they're selling hundreds at Seabird. We've built weird designs and tried to put them on stand-up paddle boards. This is the one that I'm going to talk to you a little bit more about in this talk, which is the version that's on profiling floats. We call that the deep sea Durafet. But first, I'm just going to show you one slide on kind of the history of those early pH measurements with the Durafet. And Jen may talk about this a little bit later, but we started putting these around various sites in the open ocean where pH is very stable. And then in upwelling zones along California where you see much greater excursions in pH. And in estuaries also, where you see more like tidal fluctuations in pH. And so these early measurements were really, we already kind of knew this, but this paper was one of the first ones to kind of document all these different settings in the ocean with kind of simple, same scale, 30-day snapshots of pH. We had worked with Jen to put them on coral reefs, and those went to Palmyra and Moorea, and the pH patterns look much different there. There's kind of more of a daily pattern, not the negative excursions. Some kelp forests along the California coast and Santa Barbara and La Jolla. And we also, this is my favorite, was the Antarctica work. Fortunately, I didn't get to do that, but they have even put these things underneath moving ice sheets in Antarctica. And this was the very early data set where we were excited to get the paper out, so we only had like 15 days of data. But since that, we've actually this is Gretchen Hoffman up at Santa Barbara, her group's work. They've gone back and captured entire years, and we've even captured some under ice data from floats. And this is some really weird stuff. I just labeled it extreme, but that's like CO2 vents in Italy, and I think I have one more slide from that in here. And the last thing I think I may have one more, but I want to just mention that in terms of emerging technologies beyond these pH sensors that I just showed you, there are a variety of people, and myself included. I didn't have room for myself in this slide. These are some of my colleagues. People are working on much more complicated things kind of in the micro-millifluidics realm to try to expand the measurement suite beyond just the pH and the PCO2. So we're talking about some fairly sophisticated engineering approaches to move fluids around through small manifolds and try to do benchtop chemistry at a micro scale. And I had just thrown in a couple of slides on other emerging themes. This was from a special issue in Oceanography magazine. Most of the work that I just talked about is really snapshots of ocean chemistry. But what I think people like Jen are starting to think about is how can these observations of the ocean be put into context and tested with more of a holistic view. People are beginning to acknowledge that it's not just the pH or the saturation state, but there are multiple stressors that have to be taken into account. There are advances in technology, and there are these natural analogs. So Andreas Andersen published a paper that kind of captures what I just had in that previous slide, and showing where people are doing experiments in the field of ocean acidification, kind of following that, pushing the envelope to use these different, more holistic ideas, I guess. So this was just one example of using a natural CO2 vent as an analog for a high CO2 world. Christy Croker and Theo Micheli at Stanford collected this with some sensors that we built. But this is one of those weird CO2 vent sites where you have basically CO2 bubbles coming up. This is a picture in Andreas's paper, but you can get closer to the CO2 bubbles and you can find a place where the pH is really low that might represent something, say, 100 years out from now, and you could do experiments there. You can put out plants or something next to that and maybe gain some knowledge about how those organisms would behave in a future world. So we were involved in this just to the extent that we were helping with the sensors to get the measurements, but they did all the biology. And the other kind of emerging thing, I think, is that we're building more and more sophisticated laboratory control systems now to manipulate the CO2 chemistry so that we can test multiple stressors and test things like diel cycles. And this is just one example of Lydia Kapsenberg's work, who I've worked with, putting a bunch of sensors to control a multitude of aquariums where she's growing something, and then implementing things like a mean low and a mean high pH with some diel cycle. So, all right, well, I have 15 minutes? Yes. Okay, so I'm going to just talk as fast as possible. I'm going to try to I'm just going to give an overview of some of the observing programs that have gone on in the past. And one thing I'm really excited about that just kind of found its way into this talk is the Argo observing system. So this is the cartoon that You may or may not have seen that just kind of captures all of the different ways that we observe the Earth, from the satellites to research vessels and moorings, observatories at the bottom of the ocean, free drifting things like profiling floats, AUVs, fish, I guess, I don't know. This is the traditional tool that oceanographers have used. The research vessel, that's this thing, and the rosette sampler. You guys know what that is? Have you seen the rosette sampler? So this is a bunch of bottles. They cock them open, and then they send that thing down on a winch, and they close them at different depths. Bring it back up on board. Everybody goes around in a circle. They take samples off of it. They go back to their labs, and they measure it with their benchtop measurement systems. So this is, over the last 50 years, I'm only showing back to the 1970s in this, but we've been, for about 50 years, going out on research vessels and doing a really good job of highly accurate measurements along different lines in the ocean, approximately maybe once a decade. So you might be at that particular station once a decade. This goes back to the GeoSec study, followed by the JGOFs and the WOS in the 1990s. We have an ongoing program that's currently referred to as GoShip. Was the Repeat Hydrography program, now it's GoShip, part of the CLIVAR program. Lots of acronyms to process here. But the GoShip program manages going out on these lines and sampling by ships. There are also what we call volunteer observing ships, or, because we need two acronyms for the same thing, Ship of Opportunity program. And these are on things like container ships. People go out and put these underway PCO2 systems that don't require a lot of maintenance, and they're collecting CO2 data along these lines that container ships follow. So oceanographers that are doing this type of work, and really any type of work, need to consider things like processes, how the process of interest scales over time and space. Right? So if you're interested in a phytoplankton bloom, what kind of a platform do you need in time and space to go observe that? Do you need to be on a, well, probably not a submarine. I don't know any oceanographers on submarines, but ships versus AUVs versus moorings are going to cover different time and space scales. So this is the type of thing that people that are interested in Earth system observing think a lot about, is, can my system capture the process that I'm interested in studying? And I said in this that technology is changing. Observing systems are also continuously evolving. And one thing I'd say, just since 2003, this line for floats and gliders has to really be raised all the way up to satellites, because we've had float programs in the ocean now for over a decade. So it is evolving. And this one slide I'll show about satellites, just to make note that they're very important, even in ocean acidification studies, not because we can directly observe chemistry from satellites, but we can observe ocean color beautifully and use that to coordinate with measurements in the ocean and try to expand them to a global scale. So satellites are extremely important to us in studying the Earth system as a whole, and trying to get that to work together with the ship-based measurements. This figure shows kind of all those, the two different types of repeat hydrography lines and the volunteer observing ship lines, along with a bunch of shore stations and moorings that all fall into what is known now as the Global Ocean Acidification Network, or GOON. And there are all sorts of different assets shown in this figure. The one that this figure contains is based upon just the VOS, the volunteer ship lines, and the hydrography. So 60 years of data, and PCO2 has generated an immense data set. 21.5 million PCO2 measurements have been made in the surface since 1957 that we have good confidence in. And that's generated a decent global picture on average of what the partial pressure of CO2 looks like in the ocean. This data set is compiled into seasonal averages. We call this a climatology. And data products are made to help us learn about how the different CO2 variables change throughout the year, say from February to August. This is just showing the seawater PCO2, which would reflect, if it's red, that region of the ocean is actually a source to the atmosphere, versus a blue region, which would be a sink relative to the atmosphere. So it's a little bit more complicated in terms of just treating we don't treat the whole ocean as a single source or sink. It begins to get a little bit nuanced. There are optimistic articles from time to time about how new sensors are going to solve this problem of undersampling the ocean. Here's a recent one from 2016. And I don't want to throw a wet blanket on it, but we've been saying this actually, well, you can go back 10 years, you can go back further, but the point here isn't that it's not possible to put new sensors out on these autonomous platforms, but it does take some time. So I've been working on this in this field for over 15 years now, and I've started to see that it's a very slow-moving process to actually get the sensor from the lab out onto some system like that. But I'm still optimistic about it, and seeing the pH sensors get out on these types of platforms has really given me hope that you can do it. And so I'm going to talk a little bit about the Argo program in a minute. But why autonomous platforms and sensors? I mean, I said that the space scales are challenging and difficult. I mean, the other reason is just that. It's extremely, in the Southern Ocean, for example, is really difficult to work in, right? I don't want to be there. I'm just going to give you a few examples with photos of the types of platforms that are being deployed autonomously. Moorings are currently the most widespread autonomous PCO2 measuring platform, if you're not counting underway vessels. There are, I don't know the exact number, I'm going to say approaching something like 50 moorings measuring PCO2. Most of those are operated out of the Pacific Marine Environmental Lab in Seattle, a NOAA lab. I've been working with one of these systems lately. Burke Hales at Oregon State developed, measures 2 of the CO2 parameters. And these are located at a handful of aquaculture sites along the West Coast. There's one in Carlsbad that my group helps to operate. So this is an underway shore station. It's continuously pulling water out of an aqua farm, providing the chemistry measurements in real time, hopefully to the shellfish growers. They might be able to use that for something. Maybe they can make a decision about whether or not they want to shut off their intakes. If there's this low CO2, or high CO2 event, low pH event, say there was an upwelling plume that came by, and maybe they don't want to bring water in for a day because of that. And that's actually been shown in Oregon to be a factor. More exotic platforms that we're beginning to use to observe the ocean include things like gliders that can go down and come back up in a different place by controlling their buoyancy and their pitch. These surface gliders, so we have profiling gliders and surface gliders, they've made some recent progress in putting pH and PCO2 sensors on surface gliders. We've worked in this area a little bit. The guys up at Mbari have probably done the best job, and they have this really nice figure showing this little section of the northern Monterey Bay where they've got what appears to be a pretty intense phytoplankton bloom happening, which I think all happens regularly right in that area. So that's why you have this really high pH and a high oxygen and a low PCO2. That's the hallmark of a phytoplankton bloom. Okay, so I want to close on a few things about the Argo program. I think you've already heard about this. Margaret Leinen showed at least one slide on this, but this is, my opinion, the most successful global observing system that has ever been built. It's currently over 3,800 of these drifting floats. This is in the last 30 days, how many profiles have been done. So the way, and this is a multinational program. I'm showing, I think, 25 countries here that are deploying these floats globally. And the way a profiling float works is it goes down to 1 kilometer, and it just drifts dead in the water for about 9 days. And then it turns on, and it drops to 2 kilometers. It turns on its sensors, and it comes up to the surface, measuring temperature, salinity, and pressure. And at the surface, it then sends its data to the satellites. We get it in real time. It's amazing, right? I mean, this is how we actually have been able to measure the global warming signal. We could not measure global warming until they built Argo, because over 90% of the heat due to global warming is in the ocean, but it's not all in the surface ocean. It's in the upper 1,000, 2,000 meters. And so until they could build a global system that could profile that over years, they couldn't actually parse out this heat content of the total global ocean. Atmospheric measurements are meaningless if you're trying to track the global warming signal, right? They're just an artifact of what the ocean's doing. And they've been able to show that the Southern Ocean, so the black line here, is actually taking up the bulk of the global warming signal, at least since 2006. And just to kind of drive that point home and I love hydrography programs, so I don't want to say bad things about them, but it's really just amazing when you contrast the number of temperature and salinity measurements made in 140 years to what Argo does continuously. We're talking about orders of magnitude differences, right? So something like 8,000 measurements in one of these global observing programs over 7 years versus 12,000 every month in Argo. All right. So the reason I'm talking to you about Argo in an ocean acidification lecture is that we're now building Biogeochemical-Argo, and this is adding pH sensors in particular, which is what I'm involved in. I've also worked on the oxygen some, but a variety of other bio-optical sensors, including nitrate. Here's the Durafet that I mentioned earlier on a profiling float. This is work that was led by Ken Johnson's group, my former postdoc advisor at MBARI. But these things are just now decked out with 6 or 7 different biogeochemical sensors. And I think the next slide, if I can get it, shows currently, I downloaded this yesterday. It's showing all the BioArgo floats in the array and what measurements they're making, but we've got about 74 pH measurements out in the they're almost all in the Southern Ocean right now. And this is through a program called, I don't know if I have it in here, it's in the next one, I think, that's the SOCOM program. And I just have a couple of examples. I'm trying not to run over, but this is one of my graduate students working on profiling floats under ice. So she wrote this paper where you can see the ice zone growing, and these are the locations of floats. They go under the ice for the entire ice season, and then they come back out and they send up their data. And she collected this. This is a year of, or it's actually 1.5 years. So you've got 2 ice seasons of the oxygen and the pH, and we've derived the dissolved inorganic carbon from the pH in this example. You can see a phytoplankton bloom happening right there. So this is the upper 200 meters. And we can start to do things like assess rates of plant growth and respiration. So this is plant respiration driving this line up, driving the oxygen down underneath the ice, and then the production drives the oxygen back up, and it drives this dissolved inorganic carbon back down. So starting to use these biogeochemical floats to look at rates of production and respiration in the ocean. And another example that's coming out of BioArgo now, this is similar to the version that I showed you of all the PCO2 measurements, the 21 million PCO2 measurements of the ocean, except this now shows the number of measurements made along those lines, which is not so pretty. The other one showed the actual PCO2 number, but when you look at vast areas of the ocean that only have one measurement in a given month of the year, or 1 month of data, one measurement in 1 month of the year, that makes it very hard to build climatologies. And they're now beginning to use the pH sensors on these floats to derive a PCO2 number that can compare with the climatology. And the short story here is that it doesn't always match. But they are working together. So it's not that the floats would replace the underway measurements. It's really that they would work alongside each other to improve each other. And you can think about this like this satellite picture that I showed. We're really just, the idea is you're bringing it into the Z dimension. We want to bring it below the surface that the satellites are sampling. They're just looking at the upper, really the 1/5 of the euphotic zone. So GoShip, for example, the hydrographic programs, are deploying these floats and along their lines making measurements that we can use to help calibrate and check offsets in the sensors. So you really only get one shot at that. Once the sensor's deployed, it's gone. So extremely important to be synergistic with these ship programs to get even one good pH measurement, so you can help make a traceable pH measurement that can be used in climate studies. And this is, I'm pretty much done here, but I just want to show you kind of where people are at. This is, I don't think this has been published yet, but this is some of the people working in this SOCOM program, so the Southern Ocean Climate and Observations and Modeling Program is the pilot study for the Bioargo program that I'm talking about. But these are this is the oxygen and nitrate sensor, and these are just contoured values from all of the floats that are going around the Southern Ocean right now. And what do you do with this type of data? Well, you run an ocean circulation model, so people are running climate models, and you compare the model to the data, and you use the data to constrain the model, right? That's the pie in the sky idea, is to constrain these global circulation models with the float measurements.